Hello, everyone. Welcome back to CPE 517-WS Digital and Computer System Architecture course. This is lecture 2, part 3. We're going to discuss cycle per instruction or CPI. This is your professor, Hang Liu. Okay, so the principle of computer design, the processor performance equation is shown as follows. The CPU time equals the CPU clock cycles for a program multiply the clock cycle time. So for instance, you have any program, how many clock cycles it takes to execute this program and multiply what is the real time of that clock cycle, right? And then clock cycle time is the reverse of the clock rate. Okay. Then we see CPI or cycle per instruction or cycles per instruction. It means the clock cycles for one instruction, right? So, or it's a total clock cycles for a program divided by the instruction count or IC. Putting all of them together, you can see the CPU time actually equals the instruction count multiply CPI multiply clock cycle time. Okay. A couple of things have to be kept in mind. So clock rate, what is clock rate? Okay, so here, I bet every one of you must have heard about clock rate before. So we see this is a beautiful i7 core processor, and the process speed is 3.1 gigahertz or 3 gigahertz. That 3 gigahertz is the clock rate. Okay, so it means okay. Wait. It means, let's say we have a 3 gigahertz. Everybody knows frequency, right? So gigahertz means you have these kind of things. 3 billion times, right? This is one cycle. You have 3 billion cycles per with 3 giga of such like cycles per second. Then we see what's the time for one cycle? It's definitely 1 over 3 giga, right? Okay, so 3 giga is the clock rate or the frequency of the GPU, of the CPU. Okay. So let's say if you have 1 gigahertz of the processor, that means one clock cycle is 1 nanosecond. So that's why we see you have a faster CPU typically, or we see if you have a higher frequency, it means you have faster CPU, assuming you take the same number of cycles, right? Okay. Okay, with this in mind, we can come here and see the CPU time equals the instructions per program, where we see the CPU time of a program is the total number of instructions of that program, multiply clock cycles divided by instruction, or CPI, cycle per instruction. Like how many cycles one instruction consumes, that's CPI, right? And then the time of that clock cycle was what we mentioned, 1 gigahertz means the clock cycle takes 1 nanosecond, okay? And that is the CPU time. Different instructions typically have different CPIs, right? For instance, we say division takes maybe 50 cycles, but addition takes probably 1 cycle. So that gives us a more like a rigorous or announced partition or accounting of the time consumption. So basically we get different instruction counts, like for floating point, for double floating point, for integer, we have the instruction count, and then we have a logical instruction count, et cetera, et cetera. And for every instruction type, they have typically the same, like this specific instruction type, they should have the same cycle per instruction, right? So then we have, let's say, single floating point 10, then that 10 instructions have the same CPI, and then double floating point, let's say, have 40, and then you have 40 of them have similar cycles. Then we arrive at this equation, right? So we have sigma of ICI multiply CPI I, right? For every I is 1 instruction type. And then for the CPU time, it's essentially the CPI multiply IC, then multiply the clock cycle time, because no matter what instruction it is, every clock cycle is the same, right? It's just they take different number of cycles to calculate. Okay. I think this is also a very important question, CPI. So I would also ask you guys to take 15 minutes to 20 minutes to solve this problem. Suppose we made the following measurements. The frequency of floating point operation is 25%. The average CPI of floating point is 4.0. And average CPI of the other instructions is 1.33. The frequency of floating point square root is 2%, and the CPI of this type of instruction is 20, which is very high. Assume that the 2 design alternatives are to decrease the CPI of FSQRT to 2, or to decrease the average CPI of all the floating point instructions from 4.0 to 2.5. Compare these 2 design alternatives using the process of performance equation we have discussed here. Okay.